That's all fucked up. All right. So since Dr. Richardson's not going to be here this week, I'm going to cover her lectures for this week. I am Garrett Cairo. I am a fifth-year graduate student in Tarek Semakia's lab. So before we get started, just the announcements for today. So you do have a recitation quiz this week. And if you have any Exam 1 regrade requests, do make sure to get them to me or Dr. Richardson's mailbox by Wednesday. All right. So to kind of pick up where Dr. Richardson left off, we're going to continue naming of alkenes. So sometimes, instead of having a parent chain for a molecule, it will be a parent ring instead. Number 4? I don't think so, but we can. All right, so we're going to start from number 4 instead of 5. Number substituent. So let's see. So you name the compound based on the location number, then the substituent, and then the parent. So if you have this molecule, for example, we have a vinyl group and an allo group. Depending on how we number this, we need to figure out whether we're going to number from the left to the right or from the right to the left. So if we just look at where the substituents lie, we end up with the first substituent at carbon 4, if we number starting from the left. And if we number starting from the right, we end up with our first substituent at carbon 5. So in this case, we're going to start numbering from the left, just so we end up with our substituents at the lowest numbers possible. So when we're naming this, we have an allo group. I'll go ahead and erase the incorrect numbers. We have an allo group at carbon 6 and a vinyl group at carbon 4. So we're going to list them alphabetically as we go down the list. So we'll have 6 allyl, 4 vinyl, deca, because we have a 10 carbon long chain. Then the numbers for the alkenes, remember we put the number for the alkene at the first carbon in the chain that it is interacting with. So we have an alkene starting at carbon 1 and 9. And then because we have multiple alkenes in the parent chain of this molecule, instead of just ene at the end, it will be diene. So decadiene. And the same trend would follow if we had, say, a third alkene in the parent chain as well. So, why what? Oh, so it is a diene because we have 2 alkenes in the main chain. And because we have the suffix -ene, which indicates that there is a single alkene in the molecule, diene indicates that we have two alkenes in the main chain of the molecule. Did you have a question?
Yeah, so in the textbook, it was possible to put the numbers for the double bonds in between the definite and the diene, but also in front of. And I was just wondering if there's a system that goes into that, or if it's completely arbitrary.
So in general, if you have these substituents, it's a little bit easier to keep track of where everything is in the molecule if you put the numbering as close to the functional group as possible in the name. So that just kind of makes it clearer if you have substituents that are numbered on it. You. So, for example, if we took this molecule and modified it slightly, let's remove this one so we don't end up with the wrong name. We would modify this name. We would remove the 9, and then we would remove the di. And the A. So it would be dec1ene instead, if you only have one alkene, because you still need to know where the alkene falls in the chain. Yeah, it would be decene. Or so in general, like if we had, say, a 6-membered chain. This molecule is going to be 1-hexene or hex1ene. And if we made a diene related to this one, we have alkenes at 1 and 3. So this is where we do have the A in here. So you don't need the A if you have a monoalkene. If you have a diene or a triene, then you will want to include the A. Any others before I move on to rings?
You also write the bottom symbol there as 1,3-hexadiene.
Absolutely. Yeah, there's nothing wrong with calling this one 1,3-hexadiene. And in this case, because we have no substituents, the names are pretty equivalent. All right. So in some cases, the parent in the molecule can be a ring instead of a chain. So if we want to look at an example of this, we could have a molecule like this one right here, where we don't really have any chains in this molecule. We have 1 carbon groups coming off of this ring. So instead of having a parent chain for this molecule, we will have a parent ring. And the numbering for the carbons, as far as the naming goes, is pretty similar to how it is for the chains. So you want to first have the alkene start with the lowest number possible. So we already know that we can have either this one or this one be carbon 1. So then to determine which of those we're going to start the numbering with, we will essentially figure out which one will give us the lowest numbers for the substituents on it. So I'm going to redraw the molecule so we can look at both directions without it getting too messy. So starting with this one, we know that we have to number,
Do you have to start numbering on carbon that is attached to an alkene?
You generally want to if you can, especially for the cycloalkenes. So we'll start with this one, and we do want the numbering to go through the alkene. So the second carbon that's involved in the double bond should be carbon 2 either way. And then if we wanted to number the other direction. So in this one, if we start from the left example, we have a methyl group on carbon 1 and carbon 3. Whereas if we number the other direction, we would have a methyl on carbon 2 and carbon 5. So the left one should be the one that we prefer because it gives all the substituents the lowest numbers possible. So then when we're naming this, our parent ring is going to be a cyclopentene. So essentially, because we have a ring, we add the cyclo prefix. So we know the parent molecule is cyclopent-1-ene. And then our substituents are going to be a methyl group at carbon 1 and carbon 3. So we have a 1,3-dimethyl cyclopent-1-ene. Any questions about cycloalkenes so far at all? Uh-huh.
I know on the hexanes, or sorry, the alkanes, when you have a substituent at position number 1, but you didn't need to include the number.
Mm-hmm.
In this case, since we have substituents and the allele, or with double bonds, do we need to show that one, or is it acceptable to not show it since we know we start at 1?
So because this is a ring and not a chain, it's a little less clear where it exactly starts. So you do have to define that this is carbon 1. So we have a 1,3-dimethyl for it. Because there.
I was asking about the double.
Oh, for the double bond? So you could probably get away with not including the location of the double bond because that is where we start. But if you want to be as rigorously correct as possible, you should include the numbering. Any others? Okay. So, let's see. So as the molecules get more complex, the naming gets a little more complex too. So in some cases, we will see substituents of substituents. So I'll draw up a big molecule. So we've got multiple different groups on here. The parent chain is pretty easy to point out. It's that big long one along the bottom. We know that it's the parent chain because it has the longest chain as well as the largest number of alkenes in it. So then we have these groups coming off of them that may not be the most obvious as to how to name. So you'll have to essentially do a subname inside that group. So for this first one, we already know that it's a vinyl group. But you can also call it an ethenol. So we have an alkene in there that is a 2-carbon chain, so which is where the ethene portion of that name comes from. But because it is a substituent and not the parent ring, instead of being ethene, it is ethenyl, where we remove the E and add YL to it to indicate that it is a substituent and not the parent ring. So for the next one, we have one name for it, which is allyl, but the more systematic name would be 2-propenyl. Where again, it is a propyl, it is a 3-carbon chain. And basically this number now tells us the distance from the parent chain it's from. Because we have the alkene starting on the 2nd carbon away from the parent chain, we put the 2 in here. And then when you actually include this in the name, you want to put it in parentheses to indicate that it is a somewhat complex substituent coming off of the parent chain. Contrast that, we have one that has the same number of carbons, but we've only shifted around the double bond. So where the other one was 2-propenyl, this one will be 1-propenyl. And again, in parentheses to notate that it is a substituent. And then with this one that's a little bit more complex, we have 1-ethyl ethenol. So to kind of break that down into its component parts, we have 1-ethyl, because this is the first carbon in the side chain, and ethenol, because it is a 2-carbon alkene side chain. Any questions about any of these more complex? Wait, did you have a question? Okay. Any questions about any of these nomenclature conventions?
What part of that last one is the ethyl?
So here's the ethyl, where it is just the alkane section, where it's completely saturated. And then the kind of main chain for the substituent is going to be this 2-carbon alkene right there. Any others? Okay. So now we're going to talk a little bit about kind of orbitals before we get too much further into alkenes, because they kind of help us think about how these alkenes interact and essentially how they can be different from one another even though they have the same connectivity. So if you think back to MO theory a little bit and kind of how you make the pi bond that the double bond, how you make the double bond. It is from essentially 2 unhybridized 2p orbitals where they mix constructively to give you the pi orbital, which is the double bond itself, and then the destructive interaction gives you pi star. And if we think about essentially what the p orbitals look like next to each other to have these interactions, starting with the one up top, we have a destructive interference where there is a mismatch between the lobes, which gives us the pi star orbital. Where now we have a node in the middle, just because that is inherent to the p orbitals. But because we have destructive interference between the 2 p orbitals, where the lobes are mismatched, where the positive and negative are lined up against each other, we have another node in between, where with the constructive version, we have the correct signs matching on the same side of the bond. So we get constructive interference. So because of this, because we actually have the overlap of this above and below the plane of the sigma bond, that means that alkenes are not freely rotating. So that means that essentially, if you have this alkene and this alkene, they are different molecules because we cannot rotate this group over to the other side without actually breaking that pi bond. So getting to kind of naming alkenes and how to think about alkenes, alkenes have stereoisomers based on the position of the double bond in the molecule and then the position of the substituents around the molecule. So one type of alkene isomer that you'll see is a constitutional isomer. So this is the first kind of alkene isomer that you'll see, and these are constitutional isomers. They have the same molecular formula, The difference is essentially the bonding in the molecule, where this one's 1 hexene, 2 hexene, and 3 hexene. So, like I mentioned earlier, because they are locked about that double bond and do not have free rotation, we also have stereoisomers. So essentially a stereoisomer is an isomer of a molecule where all the bonding is the same, but they have a different orientation in space. So these two molecules are good examples of stereoisomers of each other. Because they have the exact same bonding. If we look at this carbon right here, it's bonded to both a methyl group and a hydrogen, as well as the rest of the alkene. And this one's also bonded to a methyl group and a hydrogen, as well as the rest of the alkene. But the molecules behave differently and give you different products under reactions when you actually do reactions with them. So there's a couple different ways that we can kind of describe these alkenes. Just starting from these ones, this one is a cis alkene, and this one is a trans alkene. This nomenclature is essentially telling you that with the cis alkene, you have the two larger groups on the same side, and with the trans alkene, you have the two larger groups on opposite sides. And this nomenclature works fine for disubstituted alkenes, but if you get any more substitution past that, it doesn't really work anymore. So for example, if we had this molecule, so because we have 3 substituents about this alkene, we can't really use cis and trans, because cis and trans are only really useful if the alkene has 2 hydrogens on it. So instead of using cis and trans, we switch to E and Z nomenclature, where E has the 2 highest priority groups on the opposite side of the alkene, which is to say across like this plane, and where Z is where you have the 2 highest priority groups on the same side of the alkene. So that leads us to the question, how do you figure out which group is higher priority than the other? So to do that, you essentially look for the first point of difference, but we can be kind of systematic about it. So, any questions before I move on to priority? Okay. So you're essentially going to use the con-angled prelog rules to determine priority for how, like, which group is higher priority than the other. So to assign priority, what you'll do is, starting with 1, you'll move out 1 step at a time from the central carbon atom until you reach the first point of difference. So using the example that I drew just a little bit ago, we can see which one has the first point of difference a little easy. So what we want to do when we're figuring out essentially higher priority, the two carbons that we are determining priority from are the two carbons that are in the alkene right here. So we want to figure out essentially which is higher priority out of these two groups and then which is higher priority out of these two groups. So starting at the right carbon, just because it's the easiest one to kind of see the major difference at, we have a methyl group and a hydrogen. And because the methyl is bigger than the hydrogen, it'll take priority. But it gets a little less clear on the left side. So on this one, we want to look at essentially what bonds are coming off of it. I'm going to label the top group A and the bottom one B. So for A, we have this carbon right here, and we have this carbon right here. So we can't really pick which one's higher priority yet. We have to go beyond that. So going beyond that, we can see that A, the carbon bonded to A, is bonded to a carbon and two hydrogens, whereas the carbon B down here just has three hydrogens. So this means that the A group is going to be higher priority than the B group. So we have both higher priority groups on the same side in this molecule. So this one will be Z. The kind of easy way or the cheesy way to remember it is Z are on the same side. To remember that Z means that they're on the same side. Did you have a question?
With the finding the carbon
Mm-hmm.
what about that contributes to priority?
So essentially it's you look for the first point of difference. So for that example, they both go out to a single carbon, so we can't use that. So we have to go beyond that first carbon to figure out which one is higher priority. So the second in priority assignment is that higher atomic number has priority over lower atomic number. And as kind of a special condition in this one, if you have two atoms that are of the same nucleus and they are different isotopes, the heavier isotope gets priority. Do you have a question?
Yeah. Going back to that one, actually.
Uh-huh.
Why did you pick the three hydrogens on the opposite?
On this carbon right here? The one over? Because we only care about the first point of difference. And basically at this point, we can tell that this one's bonded to a carbon here while this one has no carbons. So that difference essentially ends the process for us. And we already know that A is higher priority than B.
What's the opposite of
E? The opposite of E?
like cis is the opposite of trans, what's the opposite of
Z. Z is when they're on the same side. So again, as a kind of condition to the second part of the priority determination, if you have two atoms of the same atomic number and one is a heavier isotope than the other, the heavier isotope gets priority. So for example, if we talk about just kind of 1H, protium, the most common isotope of hydrogen, versus deuterium. If we had both of those on an alkene, the deuterium would get higher priority than the protium would because it has a higher molecular mass when you have the same atomic number. And then the third one. The third one is that double bonds count as multiple bonds to the same atom when you're determining priority for a group. So if we want to look at a couple examples of these, oops, I'm already on this board. So kind of cutting the molecule in half to determine which side gets higher priority for each substituent. On the left side over here, we have a methyl versus a hydrogen, so the priority is reasonably straightforward. We have this methyl group is going to be higher priority than the hydrogen because the carbon that is directly bonded to the alkene has a higher atomic number than the hydrogen does. Moving over to the right side, we have fluorine versus carbon, and fluorine has a higher atomic number than carbon, so the fluorine will get priority here. So is this going to be an E or a Z alkene? Z, because we have the higher priority groups on the same side of the molecule. So if we want to think about another example, so this D means deuterium. So again, looking at the left, we have the central carbon is bonded to two different carbons. So we'll just label them A and B again so that we can kind of approach this problem systematically. Going out to here, we have on A bond to carbon, a bond to hydrogen, and a bond to hydrogen. And on carbon B, we simply have 3 hydrogens. So again, the ethyl group is going to get higher priority over the methyl in this case. And then on the other side, we have two atoms of the same atomic number, but we now have a different isotopic mass. So because deuterium has a neutron, which makes it heavier, and the protium does not, the deuterium will get priority over the 1H. So then, is this one going to be E or Z based on the priorities? E, because we have the higher priority groups on opposite sides of the alkene. Uh-huh.
Why did you cut those vertically when you did the first one horizontally?
So basically it's just to show it's like, all right, we're going to look at this carbon first and then the other carbon. It's basically arbitrary. Any others? Okay. Is everyone good if I erase everything on this board? All right. Okay, so moving on to a slightly more complex example. And so this one can be a little deceptive. So this one kind of drives home the point that we're looking for the first point of difference and not the physical larger size of the group. So I'm just going to label these A and B again, and then we'll work through and find the first point of difference between these two groups bonded to the left carbon of this alkene. So if we move out from the alkene up to carbon A, it has 2 bonds to carbon and then 1 bond to hydrogen there. On the bottom one, we go down to carbon, then we have 1 bond to a carbon there, but then 2 bonds to hydrogen. So we don't even have to go any further for this one to figure out which one has higher priority, because we already found the first point of difference. So out of these two, A gets the priority because it has more bonds to carbon there. So even though the B group is physically larger and has more carbons in that group, because of the substitution of the A group, it leads us to the first point of difference first, where this carbon, carbon A, has 2 bonds to carbon, giving it higher priority than the B group. Any questions about the left side so far? Okay, so then on to the right one, which is the first time we see the kind of third rule in priority assignment come into play. So I'm going to once again label these groups, group A and group B. So from carbon A, we have a bond to oxygen, and then 2 bonds to hydrogen. Whereas with the B group, we have a double bond to the oxygen. So we're going to count that as 2 bonds to oxygen as far as determining priority. So then, just kind of following like the example before, we have more bonds to oxygen than in group B than group A. So group B is going to get priority here. So then to kind of go back to the nomenclature, is this going to be an E or a Z alkene based on the priorities? Yep, E, because we have the higher priority group on the opposite side for both of these cases. So this nomenclature, just like cis and trans, does have its limitations. For example, if we had an alkene like this, we could assign priority for the left side, where the fluorine has a higher atomic number than the carbon in the methyl group, but we have 2 hydrogens on the right. So that means that neither cis-trans nomenclature or EZ nomenclature really applies to this. We just number through the chain and would say like 2-fluoropropene. So as far as applying this to naming, you can put it at the front in parentheses. So for example, if we have this molecule, so is that an E or a Z alkene just by looking at that one? E. So this one's going to be E because we have the 2 methyls on opposite sides and the hydrogens are on the opposite sides as well. And this one will be a 3-hexene because the double bond starts on carbon 3. So we would refer to this one as E3-hexene or E-hex3-ene. Going over one of the other examples, we have our parent chain being the 5-carbon chain, just kind of going through this way. And now between these 2 groups, we need to figure out which one's higher priority. So looking at the first point of difference, on the carbons directly bonded to the alkene, this one has 1 bond to carbon and 2 to hydrogen, where this one has just 3 bonds to hydrogen. So that will determine that the lower group here is going to be higher priority. So is this going to be an E or a Z alkene? Z. So when we're naming it, we have our alkene at carbon 2, and then a methyl group at carbon 3. So we can call this one Z3-methyl-pent-2-ene, or if you want to put the number in front of the pent prefix, you can do that as well. For one that has more than 1 alkene in the molecule, all of these are going to be E configured. So because we have multiple alkenes, we need to put a number in front of the E to notate both the configuration of the alkene and the location of the alkene. So we would call it 2E, 4E, 6E, 2,4,6 octatriene. Okay, so any questions about any of this nomenclature stuff before we move on to alkene stabilities? Yeah, so on the last one, so we have a triene over here, and the alkenes are at carbons 2, 4, and 6, where they start in the numbering. We know because the highest priority groups are on opposite sides in each, that each alkene in this molecule happens to be of an E configuration. So when you're actually naming it, you want to put that we have at carbon 2 an E-configured alkene, at carbon 4 an E-configured alkene, and at carbon 6 an E-configured alkene. And then the locations of the alkene followed by the parent chain name.
When you just have a chain, like how do you determine whether it's through a Z? Like what is the opposite?
So E and Z are roughly analogous to cis and trans in cases like this, where cis is Z and E is trans. So because we just have these two substituents, we do the priority basically like normal, where essentially this methyl group is going to get higher priority than the hydrogen, and then this alkene carbon is going to get higher priority than that hydrogen. So we do end up with every alkene in this molecule being of an E configuration. Any other questions before we move on?
That last one, is there a hyphen between the methyl and the N2E?
No, there's not. Any others? So essentially, if we look at this molecule, this methyl and that hydrogen are competing for priority where the methyl wins, and then we have an ethyl versus a methyl. And looking at the first point of difference, we have the ethyl taking higher priority over the methyl. And since the highest priority group on each is on the same side, we end up with it being Z. Any others?
On the triene, you have the first alkene. So to the left of that, you're comparing the carbon and the hydrogen. To the right of the molecule, you're comparing the hydrogen on the bottom to the carbon that's next to the next alkene.
Yeah.
Right? Okay.
Yeah, so essentially, this 2E is referring to this alkene right here. Any others? Okay. Is everyone all right with me erasing everything on this board? All right. So when we're talking about relative alkene stability, what we're talking about is the delta H of formation. So what that means is we're considering essentially the energetic, like how far energetically downhill it would be to construct this from its component atoms. So in general, unless you have a very unstable molecule, the delta H of formation is going to be negative, which means it's going to be energetically favorable to form the molecule. Yeah, it's the delta H of formation, which is essentially a hypothetical measurement where if you had the component atoms of the molecule and they all combined to form the molecule that you're making. Because these atoms are going to be relatively high energy. So it's essentially the energetic benefit of forming the molecule. And it's going to be different, essentially, based on the substitution and the stereochemistry of the alkene. So for example, where the y-axis is energy, we have our 4C and 4H2. There is a 1.7 kilocal per mole difference. between its component atoms and the cis alkene. So 2-cis-butene. And then a 2.72 kilcal per mole difference between its component atoms and the corresponding trans alkene. So the overall factors that impact essentially how stable a molecule is for the delta H of formation of alkenes is going to be the number of atoms in it, so a bigger molecule is going to have a bigger delta H of formation.
Can you just explain again what those numbers in the graph mean?
Yeah. They're in the literature. Essentially, they are literature reported values for the kind of combustion of the alkene compared to the starting atoms. So essentially what this is showing is that the alkene here, this cis alkene, is more stable than the just kind of starting free atoms. And then the trans alkene enjoys even more stability because we don't have essentially, if you think back to Newman projections, these ones would be essentially locked in an eclipsed conformation, whereas these two methyls are locked in an anti-conformation from each other.
The lower number, the less stable?
No, the lower number is the high stable, so is more stable. Or rather, can you repeat that? I'm not sure I understood your question.
Like the lower kilocal value, is that more stable?
Oh, no. The higher kilocal value is more stable, because if we look at this y-axis, it is the energy. And this is going to be 1.77 kilocalories per mole higher than the cis alkene, and this is going to be 2.72 kilocalories higher than the trans alkene. So essentially, it's the energy released. So the greater the magnitude of the delta HF, the more stable the molecule is.
So which one of these is more stable?
The trans, because it has the greater the magnitude of the delta H of formation. Uh-huh.
So just to clarify, the 1.77 is the delta H formation for the cis,
Yes.
and the 2.72 is the delta H formation for the trans.
Yes.
Because 2.72 releases more energy when the bonds form,
Mm-hmm.
it's more stable.
Yes. They are negative. So it's basically, you can see from the graph, this one's 2.7 lower than that. Yeah, the greater the magnitude, essentially. So you want to think about the absolute value, unless you are forming a super unstable molecule. So let's see, we've got a couple more minutes. So the next thing to consider in alkene stability is the number of groups bonded to the alkene.
What's the number of atoms versus delta?
So you're going from more hydrogens, and essentially the more carbon-hydrogen bonds you make, you're going to be releasing more energy.
And releasing more energy is less stable, right?
Releasing more energy makes it more stable, because again, we're going from the component atoms, which are going to be pretty reactive and pretty unstable. So the more energy that you release, the lower in energy the ending molecule you end up with is relative to the starting atoms. Uh-huh.
So does that mean a bigger atom is more stable?
No. No, it's not about the size of the atoms, it's more about the number of the atoms and the number of bonds that you're forming, as well as the kind of bonds you're forming. Okay, so to get back to alkene stability a little bit, we have the number of substituents impacting the stability of each alkene. So a monosubstituted alkene, something like propene, is going to be less stable than a disubstituted alkene, be it cis or trans. And then this will be even less stable. Well, yeah, this is less stable than a trisubstituted alkene. So something like this. Where essentially the greater the number of substituents on the atom there, on the alkene, the more stable the alkene is going to be. I think that's about the amount of time we have. Are there any other questions before I go teach lab? Uh-huh. Yeah.